A classic work problem in physics is the work done to empty a tank that is full of a liquid. So we're going to consider a large inverted cone-shaped tank filled with a liquid that has a density of 1,000 kilograms per meter cubed. Now that's actually the density of water. We're going to call that rho. The tank has a radius of 4 meters and a height of 12 meters. So the tank is pictured below, and it's a quite large tank that we're going to try to empty. So how much energy does it take to pump the liquid out of the tank from the top? So what we're trying to understand is that if we have, say, a horizontal slice of liquid, which has a nice thin cylindrical shape, how much work does it take to take this thin cylinder of the liquid and pump it out the top of this cone-shaped tank? So we want to lift this liquid from a height we'll call y sub k all the way to the top. Now, some features of this slice of liquid are that it's going to have a height of delta y. We're going to call the radius r sub k. Well, the work done on that specific slice in moving it to the top of the tank is going to be the force applied to that slice at y sub k times the distance that it has to travel from at the height y sub k. Okay, so the force is going to be the mass of that slice at the height y sub k times the distance that it travels, which is going to be 12 minus y sub k. Well, what is the mass? Oh, it's the mass times the gravitational constant, because the force is going to be the opposite of the force due to gravity, okay, and then times the distance. Okay, so what is the mass, though? The mass is going to be the density of the liquid times the volume of that liquid at the height y sub k. And then, of course, we still have the gravitational constant, and we still have 12 minus y sub k. So to solve this problem, we're going to have to understand what is the volume of that horizontal slice of liquid. Okay, so we're going to have rho times the volume, which is pi times the radius, r sub k squared, times the thickness, delta y. And then, of course, that mass, which is going to be density times volume, is multiplied by the gravitational constant and then multiplied by the distance traveled, 12 minus y sub k. Now, the problem here is that we have a delta y, and we have the distance in terms of y, okay, but our volume is in terms of the radius. So we need to relate the radius somehow to the height. So what I'm going to do is I'm going to imagine what happens if I slice this cone vertically so that I can look at a cross section. Okay, so that we have 4 meters across and 12 meters up and down. Then at the height y sub k, so we'll imagine that this is a total of 12 meters up and down, but there's a height here, y sub k, that there's a radius, r sub k. I'm going to make this even more clear by putting in this height of 12 meters. So again, like we did with volumes, we can use similar triangles to figure out a relationship between the radius and the height. So we know that the radius is going to be the top of one of those triangles divided by the height of that triangle. So we have the base is r sub k, the height is y sub k. And by similar triangles, that should equal the proportion, the ratio of the base of that overall triangle, which is 4 meters, over the height, which is 12. So r sub k in this case is going to be 1/3 times y sub k, solving for the radius. Okay, we can now finally say what the work is done, that is performed in lifting that one slice. It's going to be rho pi. I'm going to substitute in my 1/3 y sub k. So that's going to be 1/9 y sub k squared, because my radius was squared. And then that's going to be delta y times g times 12 minus y sub k. I'm just going to rearrange some of these constants to make things easier. So it's going to be pi rho g over 9 y sub k squared times 12 minus y sub k delta y. So that's the work in pulling this one slice up to the top and pumping it out of the tank. Well, the total work is going to be approximately the sum of the work done on each piece. And so that's going to be approximately the sum over the k's of pi rho g over 9 y sub k squared times 12 minus y sub k delta y. Okay. So what is the exact work? The exact work is going to be, of course, an integral, because that's a Riemann sum. So it's the integral from starting at 0 going up to 12 for the tank of pi rho g over 9 y squared times 12 minus y squared dy. I'm going to pull the pi rho g over 9 outside of the integral, so that I can integrate from 0 to 12, 12y squared minus y cubed dy. Well, this is going to equal pi rho g over 9. The integral, nope, I'm going to actually do the integral here. So the antiderivative there is 4y cubed minus 1/4 y to the 4th, evaluated between 0 and 12. So in fact, that's going to be pi. Rho in this case is 1,000. And then g is going to be 9.8. We're going to divide that by 9. And we're going to multiply by 4 times 12 cubed minus 12 to the 4th over 4. So if we multiply all of that out, we should get 192,000 times pi times the gravitational constant, joules, or if we want to work it out, that's going to be 5,911,221 if I round to the nearest 1 joules. And that's the amount of work that it takes to lift the water out of the tank and empty it completely.